Hello, can you please confirm if I'm audible? Okay, yeah, thank you. So maybe I think we can start. Let the participants join later. So welcome to the live session for week 3 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. I'm Anant Singhal, a PhD student from IIT Jodhpur, and today I'll be assisting you in solving some of the similar assignment problems that have been given to you in your week 3 assignments. So till now, I think in the previous two lectures we have already established like the very basic of the of this particular course, like what is modeling, why do we require modeling, and some of the very basic of the silicon, that is what is the crystal structure, how do we deal with it, and some of the things such as doping, what is the band structure of the silicon, what is the effective mass, let's say in terms of electrons and holes. I would say today is the most important lecture for this whole course because today we'll be dealing with the density of states, electron mobility. So these are some of the concepts that actually are applicable to any of the device that we'll be studying in this course. For example, we'll be studying PN junction, as you can see in week 4. It is written PN junction. Week 5 it is written BJT. Then week 6 we have MOSFET and MOSCAP. So all of this revolves around the concept which is derived from itself, the density of states, mobility, what is this Fermi Dirac distribution or the Fermi Dirac function, and how do we calculate all of this. So yeah, I would say today is the most important lecture for this course, and maybe we can start with some of the topics that are quite important in this particular week. So I think we can start. So so yeah, the most basic topic would be that I'll be starting with is the electric field intensity. So we'll solve some of the problems related to all of these topics, and side by side we'll also cover the concepts that will help you in solving those problems. So what is electric field intensity? Let me try to explain in very basic words as of now. So let's say since we are talking about silicon here, let's say we have a semiconductor bar which is made up of silicon. Let's say this is a semiconductor bar and it is made up of a silicon. And what we do is we apply a certain voltage which is, let's say, V volt. So let's say this is a silicon bar and it has a length of L. So what we see here is a positive voltage. So let's say this is at x is equals to 0 and this is x is equal to L, right? So electric field, what electric field is? Electric field is always from the higher potential, sorry, to the lower potential. So it should be like this, right? So if I try to make it in this form of silicon bar, it should be from higher potential to the lower potential. So if electric field is now nothing but the change in voltage with respect to the position. So if I try to, let's say, take at for this particular example, if I say that at x is equals to 0, we have, so minus I'll take here, at x equals to 0, we have a voltage of 0. Sorry, we have, yeah, and at corresponding at x is equals to L, what do we have? We have a voltage of V because this is the V, right? So if I try to solve it, this would come out to be something minus V by L. So this is with respect to this particular example only, it is nothing but the change in voltage with respect to the position is what we call as the electric field. And now we know that once we apply any electric field, I think we discussed this in the last lecture, that there would be a force that is being felt by both due to electrons and holes, and this force would be nothing but charge times the electric field. So now if I talk in terms of electrons, in electrons, we know that the charge is negative, right? So let me write minus Q because of the negative charge times electric field. So this negative, what does it say? That let's say our electric field is from higher potential to lower potential. So the force that will be felt by the electrons is always in the opposite direction due to this negative sign. So this will be the direction of the force, or the electron will feel the force in this direction. And if I say the same about holes, now we know that the hole has a positive charge, right? So if the electric field is from higher potential to lower potential, the holes will also go from or feel the force from higher potential to lower potential, right? So this is a very basic concept of what electric field is. And So the mobility is what the first topic of this lecture is. So let me see. Let us see that how does it come from. So it comes from the velocity of carriers. So I hope that you know that current is nothing but the flow of charge, right? So we can calculate current with respect to charge times what is the velocity. So this is a very basic formula of current. So it depends upon the charge and how what they are flowing. So this is the electrostatic part, and this is the transport part. So we just need to figure out which we can make better, and this is how we can make any device have a higher current flow. So velocity of carriers, now it is basically dependent upon two main phenomena. The first one would be thermal velocity, and the second one would be drift velocity. So as the name suggests, the thermal velocity will be due to the application of temperature or the heating. So I'll try to explain in detail. And the drift velocity, it comes from due to the application of electric field. So these are the two main velocity. So let me discuss about the thermal velocity first. So thermal velocity, as I said, this is due to temperature. Let's say we have a temperature T, for example. So we know that the energy, according to the Boltzmann constant, it should be around 3 by 2 kT. So this is the very basic formula that we already know. And now since the electrons have motion and it has some kinetic energy that we have as half mv square. So if I try to equate this energy with respect to the thermal energy, which is 3 by 2 kT, and now try to find out the velocity. So this 2 will get cancelled out. It will come out to be, sorry, it will come out to be 3 kT by m, right? So m, let's say even we keep it as effective mass since we are talking in terms of effective mass from the last class. So we have all those values. So we know k is a Boltzmann constant. We know this k is a Boltzmann constant, which is nothing but I think it's 1.38 times per 23 or minus 23 joule per Kelvin. Then we also have this temperature. Let's say we are talking about 300 Kelvin as of now, and mass we know. For example, we are taking minus 31 kg. So if we try to feed this thermal velocity here, it would come out to be, I'm not doing the calculation, but it will come out to be, you can do it your own end, approximately 10 raised per 5 meter per second, or I can say the thermal velocity to be 10 raised per 7 centimeter per second, right? So due to the application of temperatures, this is what we can achieve. I'm talking about at room temperature. So this is the saturation that we cannot have a speed higher than that of 10 raised per 7 centimeter per second. Why? Because let's say we apply some, let me try to explain this. So let's say we apply some, we have a speed of light as we know 310 raised per 8 meter per second, right? So let's say there is this electron due to the temperature, it does? It goes here, then it goes here. So there is this random displacement, right? So it is going in random directions. And what happens? At last, we have a net displacement of zero. So this electron came back here, due to which we have a net displacement of zero. So why it is getting net displacement of zero? Because this electron is getting uh, is colliding with the other particles that are present in the silicon surface. So there is one more term which is the average collision time, that is between one electron to the one particle, is given by tau c. So it would be, I mean, I'll try to explain that concept later. But this is the thermal velocity, and there is net zero displacement because we have not applied any electric field. So the displacement would be zero. So similarly, so this is a thermal limit, right? We cannot go beyond. So I'm talking about at 300 Kelvin. So now the second part would be, if I, let's say if I do apply some velocity, which would be coming due to the application of electric field, right? As I said, it is the drift velocity. Yeah. So let's say we have again a silicon semiconductor bar, We have discussed the electric field is from higher to lower potential, so it would be like this. We know the electron phase force in the opposite direction and hole phase force in the field force in the same direction. So now, as we apply the electric field, we know that force is nothing but mass into acceleration, right? So as we see that if we are applying on F, we have just established is Q into E. So as we are applying the electric field, ideally, what do we have? We should have more acceleration of the electrons, right? But this case is only applicable when we have a vacuum. So for example, let's say we have a structure something like this. Let's say this is silicon and we have a lot of silicon atoms into it, right? So let's say I'm talking about, let's say this electron is going here. Now, due to this vibrations, that is what we call as phonon, or due to the application of electric field, let's say this is from higher potential to lower potential. Let's say if I say in this direction, so what will happen? This electron will go here and it will collide from this, right? So we have applied some electric field. There is some force due to which there is some acceleration, but due to the collision, it has deaccelerated, right? Because we are so let's say this gets collided here, so this has some lesser speed now. Now it is going from here to here, and it is again colliding, and this is how it is coming out. So you see, the acceleration is not constant, or acceleration is not always there when we are talking about in terms of a crystal. It's not like a vacuum that the acceleration will always happen. So this is why what we are learning about the concept of velocity, not the acceleration. So as soon as we apply some thermal energy, what we know that there is lattice vibrations also. These atoms will move in some uh, zigzag or the ziggling position is what we call as. And due to this vibration, these electron will get collide more further, right? Hence, what do we have is there is no net acceleration in this due to this collision. There is deceleration. So it is like electron is accelerating, then it is colliding, it is coming into the rest, it is accelerating again, again coming into the rest. Due to which, what do we have? We have a constant velocity. That is what we are terming as drift velocity. And what we are saying that this drift velocity is nothing but a function of electric field. And in general, we write this constant as mobility. So, is there any doubt in this how this drift velocity comes from? Okay. So, so since we'll be doing some numerical, so we need to have some values handy. So this is the mobility, as I said. Yes. Yes. Okay. 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 So actually, the slots get decided before even the course starts. So I mean, the possibility is not there that we can shift this. So hmm. Yeah, yeah. So I completely understand that you have two courses that are colliding the exact same time, right? The tutorials. Yeah. So I mean, from my side, I cannot do that because I mean, you can raise your request to the NPTEL team if they can allow. So you can even have that machine learning session to the Sundays. And if that also not works, then we have the videos that are being uploaded over YouTube. So you can see those videos just after the lecture ends. Yeah, no problem. So as I was saying that we are will be dealing from yeah, so we'll be dealing for silicon. So we need to be handy about some values for mobility. So for silicon, the mobility value for the electrons is around 1300 centimeters square per volt second. So you should always remembering these units because this will help you in solving numericals and also help you remember the formulas. The mobility of holes is around 500 centimeters square per volt second. So now as you can see, what do we have? Vd is equals to mu e. So let's say if I want to plot, so let's try to answer this question. Let's say if I want to plot the drift velocity as a function of electric field. So what do you think the nature of this plot would be? Any idea? Anyone wants to take a guess? Yeah, so it is like a function which is y is equals to mx. So ideally, what it should be like a straight line. So as we are increasing the electric field, our drift velocity is increasing. So that means the slope of this would be mobility, right? But now we have also read that there is a thermal limit that the electron cannot have or cannot attain a speed which is greater than that of the thermal velocity. So let's say that velocity is around here, which is I'm denoting with as VTH. Let's say this is, for example, 10 to the power 7 centimeter per second. So it will increase, but since we know that the electron cannot achieve a velocity greater than that of the thermal velocity, so it will saturate at some point. So this is how actually a VD versus electric field curves look like. So in this region, as you increase the electric field, your VD will increase. But in this region, what happens is as you increase the electric field, your VD is constant. That basically means your mobility is decreasing, right? Because this should decrease and this should increase, then only this will become constant. Are you all able to understand this plot? Why? Yeah, so yes, exactly. Because to keep this constant, if you're increasing a quantity, we need to decrease this. That is what I am saying that as we increase the temperature, uh, there will be more scattering and the mobility or the collisions would be more and the mobility would decrease. Hence, we have a VD as constant because mobility is decreasing and electric field is increasing. So this is applicable for this region, and in this region, as the electric field is increasing, the VD is increasing because here the mobility is constant. Is this clear to everyone? Okay. So let's try to have a problem related to this, which is this one, I guess. So the problem says what do we have is the dependence of the drift velocity on the electric field of n type semiconductor is given below. So we have a certain values that are given. So this is in centimeter per second, this is in volt per centimeter. It says we have a n-type silicon with majority carrier concentration. So that would be Nd that we discussed in the last lecture is biased with 1 volt source across a length of 1 micrometer. You need to find the drift velocity. So this is actually a very easy problem. I would like you should all take maybe 5 or 2 to 3 minutes and try to give answers in the chat box. Yes, is there any doubt? Okay, yeah. So try to solve this problem and type your answers in the chat box. Anyone got any answer? Okay, so this was a easy problem, so let me try to solve it. So what do we need to calculate? We need to calculate the drift velocity, right? We just established it is nothing but mu e, and e is nothing but the change with respect to voltage with respect to the length. So we have 1 volt for 1 micrometer. So we have 1 volt by 1 micrometer. So it is given per centimeter. So everything you see is in centimeter, right? So let me write V by L. So it's 1 volt and this is 1 micrometer. So I can write this as 1 by 10 to the power minus 4 centimeter. That will give me the electric field to be, let me write in raised to power 4 only, 10 to the power 4 volt per centimeter. So now the second thing that we want here is mobility, right? So mobility is nothing but the slope of this. So if I try to calculate mobility, so at 1 into 10 to the power 5 volt per centimeter, this is 10 to the power 7 and this is 0 comma 0, right? So slope basic mathematics is y2 minus y1 over x2 minus x1, right? So it would be 10 to the power 7 minus 0 and 10 to the power 5 minus 0, and this would be in centimeter square per volt second. Is there any doubt in this? How I've calculated the mobility? Oh, this value is 1 and this is in 10 to the power 5. So this value is actually 10 to the power 5 volt per centimeter. Yeah. So the mobility will come out to be 100 centimeter square per volt second. So now we need to calculate the drift velocity, and this is nothing but mu. Yeah, so it will come out to be 10 to the power 6 centimeter square per volt second, which is option D. Sorry, it is a velocity, so this should be centimeter per second. So you need to be very careful about the units because it is meter also given in the question. So 10 to the power 6 centimeter per second will be 10 to the power 4 meter per second. But since the answer is in centimeter itself, so we do not need to worry about for this particular problem. Is it clear to everyone? Okay, so if this is clear, then let me try to give you one easy problem again. So let's say we have a 10 volt application of over a silicon. So silicon, let's say, I mean, just to easy or simplify, let's say we take the mobility as 1000 centimeter square per volt second, and the length of the silicon bar is, let's say, 1 centimeter, and the doping concentration, let's say, if I give at 10 to the power 16 per centimeter cube. So what do we need to time? We need to find that average collision time. As I told you in the previous, when I was explaining this concept today only, I told you that collision time will be nothing but the distance divided by the velocity. I mean, the common formula is distance is speed into time. So what we need to calculate? We need to calculate this. So we have L, we'll calculate the VD and then we calculate the final time. This is actually again a very easy problem. So maybe you can take 2 minutes and quickly let me know what is the answer. So again, any answer? This was supposed to be a easier one. Anybody who was able to calculate VD? So this is mu E, right? Mu is given. We need to find E. E is what? V by L. So V is given 10 volts. L is given 1. So this is 10 volt. Yeah, yeah. So VD would be 10 times 1000, which is 10 is per 4 centimeter per second. Now you just need to calculate the time, which will be 1 centimeter divided by 10 to the power 4 centimeter per second. So the time would be 10 is per minus 4 seconds. And we can write this as 100 microseconds also. Is this clear to everyone? Okay. So try to solve on your own. I mean, these are quite easy problems. I'm trying to build your concept so that you will be able to solve the assignment problems also. So let's do one more quickly. Now it says the dependent upon the drift velocity is shown below. The plot is same, but here what do we have is we have a majority carrier concentration of this. We need to calculate the current density. So has anybody having any idea what is current density? It's, yeah, so it is I by A, that is correct. So it all comes from the current formula, which is NEAVD. And here I by A is the current density, which comes out to be NEVD, where N is the concentration, E is the charge, VD is the drift velocity. And we just established what is VD. VD is mu E. So it would be N E mu E. And this is what we call as Ohm's law also. You should have seen J is equals to sigma E. So this sigma is nothing but this term. In general, what do we write it as? NQ mu E. So we denote charge by Q, not by E. Is there any doubt in this? So if not, you just need to calculate J. So I think you have everything in the question. So quickly let me know what is the answer. Maybe you can take 2 minutes and let me know what is the answer. So still no answer. Okay, so let me try. So what we do, we need to calculate, the current density, which is n q mu e. So now n is the concentration, which is given as 10 is per 30. Charge, we know it's 1.6 minus 19. Mobility is not given, so again it is a slope. So we just calculated it as minus 0 divided by 10 is per 5 minus 0. It was 100. So it's 100. Electric field, is it given? Electric field is nothing but V by L. So it's, yeah, so it should be in centimeters. So it should be 10 per minus 4. Yeah. So this should be minus 2 minus 17 minus 4. So this is 1300. Oh, so this should be plus 4, not minus 4. 690. So yeah, it should come out to be 1.6, if I'm not wrong, ampere per centimeter square, which is option C. Is this clear? Okay, so I would like to emphasize again that this thing is nothing but sigma. So this is what we have as the Ohm's law. This is J is equals to sigma E. So sigma would be nothing but NQ mu. So why I'm emphasizing it? Because of this problem. So it says we need to calculate the conductivity. Conductivity is nothing but sigma of a semiconductor which is doped with this amount of pentavalent impurities. Mobility is given, mobility of hole is given, and Ni is given. So maybe you can take 1 or 2 minutes and let me know the answer. So this is again a similar problem that we are doing from the past 10 minutes. So do let me know if you are able to solve it and type your answers in the chat box. Okay, so even before starting, can anyone tell what do we mean by pentavalent impurities? We discussed this in the last lecture. Yeah, N-type. That is good. So N-type impurities are group 5 impurities, and hence since they have extra electrons, so hence they are N-type impurities. So this value that is stands for 16 is nothing but N, or ND to be precise. So yeah, now you can try the problem. It should not take more than 2 minutes, and type your answers in the chat box. Okay, so let's try to solve it side by side. So what do we need to calculate? We need to calculate sigma, right? So as I said, sigma is NQ mu N. So here I'd like to emphasize one more thing, that we have a whole mobility also given here. But you see the electron concentration, that is ND, is approximately 10 is per 16 per centimeter cube. So we know that as per mass action law, what do we have? Np as Ni square. And Ni is given as 10 per 10. So if I try to calculate the whole concentration, this will come out to be 10 per 4. Yeah. So what this is meaning, actually the whole conductivity is nothing but Nq mu n plus Pq mu p, right? Because the actual J that we were calculating is for both electron and holes. So if I try to expand this is Nq mu n plus Pq mu p times E. But since this 10 per 4 is very less as compared to 10 per 16, we are kind of neglecting this. Hence the formula that we have written is only Nq mu n, or we have written J as Nq mu n times E. Is this clear to everyone? Okay. So if this is clear, then this was a very easy problem. So let's try to find it out. So n is given by here 10 per 16. Q we have already, sorry, this is 1.6, 10 per minus 19. Then we have mu n. Mu n is given as 1800. So we need to calculate the whole, oh sorry, the electron mobility, right? Because we are dealing with the pentavalent or the n-type impurities. And then electric field, is it given? Electric field is, oh, electric field is not given. Oh, we don't need to calculate the electricity, sorry. We want only the conductivity, not the sigma J value. So this is the actual answer. So if I try to find out, so this is 18, this would be minus 1. So it would be 1.6 times 1.8, which is 256 plus 32, 2.88. So this should be the answer. Now please let me know if you have any doubt regarding anything till we have done till now. So we have kind of covered the concept around the mobility, how does it come into the picture, and why this actual curve saturates this VD is equals to mu E plot. So this is a major takeaway of this particular problems, that why do we have a saturation, and what is drift velocity and what is actually the thermal velocity. So is there any doubt till now? Anyone having any doubts? Okay, that's great. So let's move ahead to the maybe the most important topic for this course, which is nothing but the Fermi-Dirac distribution function. Anyone having any idea already? What is this Fermi-Dirac distribution function? Sorry, anyone wants to take a guess? Even just okay. So let me give you the expression that maybe you might remember. So it's nothing but one plus exponential E minus EF over KT. So does anyone know what is this FE? Yeah, so what does this Fe actually, I mean, what do we calculate using this Fe? Yes, Fe is a Fermi function, but what are we trying to find using this? That is the question. Yes, exactly. So Fe is actually the probability of, as she said, probability of finding an electron at energy level E and at temperature T. So these are the two things that are variable here. One is this E, sorry, one is this E, which is here, and one is this T, which is here. And now if I ask you what is 1 minus Fe, what would be the 1 minus Fe term? Yeah, exactly. So we say it probability of finding holes, because we do establish that wherever there is a vacancy of electron, it is nothing but holes at energy E and temperature T. So these are the two things that we are trying to calculate using this Fermi Dirac distribution. And in the first lecture, if you remember, we studied about this Pauli's, oh sorry, not Pauli's, but Heisenberg uncertainty principle, in which we figured out that we cannot find the position or the momentum simultaneously. So we just try to find the probability of electron anywhere. So that is what the concept of semiconductor is. There is no certainty. We just use the concept of probability to find whether the electron is there or not. So this is what the Fermi Dirac distribution function does. And let's try to have some more cases regarding this. So let's say if I take the first case, that we have a temperature which is not equals to zero, but the energy level is equals to Fermi level. So if I try to calculate Fe, it would be nothing but 1 upon 1 plus exponential. What would be the exponential term? If E is equals to EF and temperature is not equals to zero. Yeah, so it would be exponential 0 and that would be 1. So that means, so the Fermi Dirac, we can also say that it is the probability where the probability of finding an electron is always 1 by 2. So this is at EF. So we can define Fermi level by this definition, that Fermi level is that energy level where the probability of finding an electron is always 1 by 2. Are you trying to understand this, all of you? So okay, so Fermi level, I'm trying to define Fermi level here. So Fermi level is that energy level at which the probability of finding the electron is always 1 by 2. Make sense? Yeah. So now if I say that let's say I'm talking about 0 Kelvin now. Okay, wait. Let's say I'm talking about 0 Kelvin now. Yeah. So let's say at T is equals to 0 Kelvin, and I'm talking about at energy level which is greater than that of Fermi. So if I try to calculate Fe here, so what will be the Fe? It is 1 upon 1 plus exponential E minus EF over KT. So can anyone tell what would be this term if I put these conditions? This would be 1 upon 1 plus what? Yeah, so it would be e raised to power infinity, which is again infinity. So it would be 1 by infinity, which is 0, right? And similarly, if I say that the temperature is still at 0 Kelvin, but the energy level is now lying below the Fermi level, then the Fe would be what? 1 upon 1 plus, yeah, e power minus infinity is 0, right? So it would be 1 upon 1 plus 0, that means 1. So now, if you remember in the first class, what I said was, let's say this is the energy level, which is called as EF. So now what we are getting, that energy level below the EF, all the probability of finding electron below EF is always 1. That means it is completely filled. And the probability of finding electron above Fermi level is 0. That means it is completely empty. Do you remember this? That we discussed this in the first lecture, and this is how it comes from. I mean, this is the relation between the physics and the mathematics. Are you all able to understand this? What I'm trying to say? Okay. So if I now, I mean, even let's have more clarification. Now, if I try to plot Fermi Dirac function with respect to energy only. So we have just seen that at, so I'm drawing it for temperature equals to 0 Kelvin as of now. So below EF, the probability of finding electron is 1. After EF, it is 0. So this is 0, this is 1. Are you all able to understand this plot? Yes, yes. Yes, yeah, sure, sure. So as I said, at E greater than EF, this value would be positive by 0. So that was e raised power infinity. So as I'm saying that at any level of energy which is above the Fermi level, the probability of finding the electron is coming out to be zero. That means it is empty. Similarly, as I said that at any energy level which is below that EF, the probability of finding electron is coming out to be 1. So that means it is completely filled, right? So this was the first case in which it was e raised power infinity, it was 0. And for the case when temperature is equal to 0 as well as E is less than EF, the Fermi energy was 1. So this is what I just draw. So if I plot the Fermi with respect to energy, so I said below EF, the probability of finding electron is always 1, and after EF, it is always 0. So this is 1, this is 0. Make sense now? Yeah, and one more thing that I am saying now that uh, as we are applying a certain energy, that is when we are taking the electrons, let's say these are the electrons, this is the valence band, and this is the conduction band, for example. So we do apply some energy so that this electron from valence band goes to the conduction band. So this is how it is done at any finite temperature, right? Let's say it is at T1 Kelvin. So if I try to increase the temperature, what would happen? The probability of finding electron below EF would decrease, right? And it tried to increase after EF. So this is the actual plot which is at any temperature T1 Kelvin. Is this purple plot clear to everyone? So let's say even if I now take T2 temperature which is even greater than T1. So how would you think that the plot should come like? More steeper or more flatter? Steeper means down or up? Yeah, yeah. So more down, that means the probability would even decrease for below Fermi and it should even increase for above Fermi. So this temperature should be T2. Is it clear to everyone what we are trying to establish here? This is more physical than mathematical. As we are increasing the temperature, we know that the electron will go from valence to conduction band, hence we are having a lower probability. Any doubts, anyone? Because this is very important. I mean, everything will be derived using the Fermi Dirac distribution function only. So you should be aware of this concept, and you should never forget this. That is why I'm emphasizing again. Is there any doubt? Okay, that's great. So now the problem with this is highly complex. So what we do is we do some approximations just to have some easy derivations. So one such approximation that we do is what we call as the Boltzmann approximation. So let's do that too. So by Boltzmann approximation, what do we do is we say that if this energy level E minus EF is very, very greater than KT, and in general, what we consider is if this E minus EF is greater than 3 kT. So this Fermi Dirac distribution function, which is something like 1 upon 1 plus exponential of E minus EF over KT. So if this thing is very, very greater than KT, so that means if exponential of maybe, yeah, this exponential term is very, very greater than, so can I say this term will be very, very greater than 1? Yes or no? Anyone? Is it not clear? Okay, so I'm saying that this E minus EF, I'm taking the case it is very, very greater than KT. So this exponential of E minus EF over KT, it is like E raised to power 3 or greater than that, right? And what I'm trying to ask is is this greater than 1? Is it very, very greater than 1? Yeah, so hence what do we do is we neglect this one and we write this as 1 upon exponential of E minus EF over KT. And hence the Fermi Dirac distribution function just comes out to be e raised to power minus E minus EF over KT. So this is the Boltzmann approximation that we in general study in the uh, normal standard books. So if you have read about Niemann or Charles Kittle or any book, this is what the formula is written there. Similarly, if I can do the second case, that when E minus EF is very less than KT. So using this, we in general calculate the probability of holes because the electron or the energy level is actually very close to the Fermi level. So if I try to do this again, it should be something like this. So this should give me exponential of E minus EF over KT divided by 1 plus this term only, this. So again, this would be very less than 1. So the 1 minus Fe comes out to be exponential of E minus EF over KT. So these are the two cases that we need to see. Is the concept of Fermi level clear to everyone now? If you have any doubt, please ask. Okay, yeah, so that's great. So let's do a problem maybe. Let's see how much is it is clear to everyone. Yes, yes. Yeah. Yeah, less than, yeah, I can say, yeah. I am saying that it is less than 3 kT. Very less means it is less than 3 kT. So the expression was positive E minus EF. For Fe it was exponential of minus E minus EF. So if this is clear, I mean, even if the Fermi Dirac is clear, let me try to ask you a problem. So it would be great if we can solve it simultaneously. Let's say I have a Fermi level at 5.5 electron volt. Now the question is we need to find the temperature at which, try to understand the problem thoroughly, at which there is a probability of 2% that a state which is 0.25 electron volt below than Fermi level will be empty of electron. So let me again reiterate the question because this is, so I have given you a Fermi level. I want a temperature at which the probability, there is a probability of 2% and that the state which is 0.25 below the Fermi level will be empty of an electron. So the three keywords in this problem is, one is empty of an electron, one is which is 0.25 below the Fermi level, and the Fermi level. So can anyone tell me what is this 2%? If you understand the concept, you should be able to tell. Anyone wants to take a guess? Is the question not clear to anyone, or are you trying to think it? Okay, so let me ask you in opposite way. Yeah. So could you please mute your mic? Yeah. So what was Fe? What was the definition of the Fe? Anyone quickly? No, I'm not asking. No, I'm not asking the. Yeah. What was Fe? Yeah. Yes, it was probability of energy state filled with electron, right? I have given that the probability of 2% that it is empty of an electron. So what is this 2%? So empty of electron means holes, right? So it would be occupied with holes. So what is 2%? Again, my question is what is 2%? Sorry? Uh, so you are not on mute. So is this? Yeah. So what will be this 2%? Again, my question is this. 2% is the probability that it is occupied with holes. Exactly. So 1 minus f of v is 2%. And the second thing that is given in the question is the energy state is 0.25 volt below the Fermi level. So let's say this is the Fermi level and this is my energy state. So it is 0.25 electron volt below. So can I say my E minus EF is minus 0.25 electron volt? Can I say this? Just to be easy. Yeah. So EF minus E is actually 0.25 electron volt. So if you know all of this, this is very easy to solve. I mean, these are the two things that you need to understand. So we already know what is Fe. So 1 minus Fe is 2%. We know what is Fe, right? Fe is 1 upon 1 plus exponential of that term. I'm not writing it as of now. So it would be exponential of E minus Ef over kT, 1 plus exponential of E minus Ef over kT. And this is 2%, which is 2 by 100. Okay, and if I try to write this in, this will come out to be 1 upon 1 plus exponential of minus E minus Ef over kT, which is 2 by 100. And we already know what is this. 1 upon exponential minus E minus Ef is already given to us, which is minus 0.25 over kT, which is 2 by 100. So I can write this as 1 upon 1 plus exponential 0.25 over kT, 2 by 100. We need to find T and K. We already know it is a Boltzmann constant, right? So K is 1.38 times power 23, sorry, minus 23 joules per Kelvin. And if we try to solve it in electron volt, this is 8.62 times per minus 5 electron volt per Kelvin. Since everything is electron volt here, so we can write, so this would be 1 by 50, 50 minus 1 will be 49. So we can write exponential of 0.25 over kT is 49. And if we take log on the both sides, this will be 0.25 over kT is ln 49. Are you all able to understand these calculations? Any doubts? The temperature would be 0.25 times K, which is 8.62 minus 5 times ln 49. So this would be your final answer, which should be in Kelvin. Any doubts, anyone? So this should come out to be, I've done the calculation, so this should be 745.2 Kelvin. You can try at your homes also. The major objective was to should be that you should be able to understand these things. Is it clear? Shall we move ahead? Okay, so let's see the final concept maybe quickly because we are running out of time. So I'll not do the density of states derivation because we don't have much time, but let me write the formulas for the electron and the hole concentration directly so that we will be able to solve some problems. So there are two types of formulas. One is the type which is having the effective density of states, and one type which is having the intrinsic concentration. So it is minus EC minus EF over KT. This is EF minus EI over KT. Similarly, for holes, we have effective density of states of valence band exponential of EF minus EB over KT, and this is Ni exponential of EI minus EF over KT. So these four formulas you should always remember in the semiconductor device physics. So there is one way to understand this. So quickly tell me, is N bigger or Ni bigger? Anyone? N is, yeah, N is bigger, right? So for why N is bigger? Because we have a N type of concentration and Ni is let's say in the order of 10 to the power 10. So for this, since N is bigger, we need to have this term as positive, right? And for this term to be positive, we need to have the Fermi level, which is above than that of the intrinsic level, because this is an n-type impurity. So Fermi level should be close to the conduction band. So this is one way you can remember this formula, what comes first. So since N is bigger, so EF minus EI is positive. Similarly, you can do for P also. And so as I said, there are two things that we can calculate. One is the difference between the conduction band and the Fermi band, which is EC minus EF. And one is the difference between the Fermi and the intrinsic, which is EF minus EI. So these are the two formulas that we can use to calculate anything. Any doubts in here? Okay, so if not, quickly let me know the answer to this. First of all, tell me what do we need to calculate. So it says calculate the shift in the intrinsic level when the semiconductor is doped with pentavalent impurities of doping this. So what it is asking? Anyone? Can anyone tell what the question is asking? Hmm. Hmm. Yeah. Exactly. So what it is asking is the Fermi level, how much is it shifted from the intrinsic level? So this is the question, right? Are you all able to understand that it is asking EF minus EI? Yeah. So quickly calculate. This is a very easy problem then. So it's pentavalent. That means it is N type. So I can use this formula. N is Ni exponential of EF minus EI over KT. Everything is given. You just need to put in the formula. Quickly let me know the answer. Maybe you can take 2 3 minutes and then let me know the answer. So in easier form, we can also write EF minus EI as KT ln mm, N over Ni. You can take log at both the sides, you will get this. So you have everything given in the question. So this is 26 milli electron volt. N is Nd. Which option? Okay, so yeah, let me to calculate. So it's 0.06 times ln times per 5, it should be around, this is a 30, 0.13 ln 10. This should be 0.13 into 2.303. Yeah, it should be around zero point 0.3. That is correct. So yeah, option A is the correct answer. Is this clear to everyone? So let's cover one more concept and then maybe. Yeah, so let's cover one more concept quickly and then we can wrap up the class. So we have just seen that we have one n which is nc exponential of minus ec minus ef over kt. We have p which is nv exponential of ef minus ev over kt. And at equilibrium, what do we know? What is the mass action law? Anyone quickly tell me what is the mass action law? Yeah. So if I try to put this n and p here, so I will get nc times, or nv I can also take common, exponential of minus ec plus ef over kt exponential of ef minus ev over kt is equals to ni square, right? So what is exponential a times exponential b? What is the formula? Exponential of a plus b, right? So if we know this, so can I write NCNV exponential of, yeah, EF will cancel out and it will come out to be minus EC, yeah, so plus EV equals to NI square. And if I draw this EC, this is EV. So what is EC minus EV? Exactly. So it should be NCNV exponential of minus the band gap which is EG over KT. So I can calculate NI easily from here, which is under root NCNV exponential of minus Eg over 2kt. Is this clear to everyone? This is only applicable at equilibrium only. Any doubts in this? Oh, because of this under root. So I need to put under root, right? So if this has a power of 1 by 2, this 2 will come down, right? Yeah. Any doubts, anyone? If not, okay, quickly let me know the answer to this. This would be the last problem for today, and then maybe we can continue in next week. So it says we have two semiconductors which are A and B, which have identical band structure except for their band gap. So material A has a band gap of 1, while the material B has a band gap of 1.2. We need to determine the ratio of the intrinsic concentration, which is this, of material A to B. So we need to calculate Ni of A ratio to Ni of B. So this is the question. So what should be the answer? I mean, in shortcut, if I try to say. So can I write, since they have identical band structure, NB and C exponential of minus Eg 1 over 2 kt, because they have different band gaps, divided by NCNV exponential of minus Eg2 over kt. Can I write this? Yeah. So if I divide this, the only term that we are left with is, should be minus Eg1 plus Eg2 over kt, right? And we already know the value, so it should be exponential of minus 1.0 plus 1.2 over kt. So this should be e raised power 0.2 divided by 0.026, because we have been given this. This should be the answer, which should be, I don't, okay. So 46.8, option D is the right answer. So are these concepts clear to everyone? How we have calculated the Fermi and what is Boltzmann approximation? What is this mass action law? What is the mobility? Why does it saturate? What are the two types of velocity components? Is there any doubt in all of this? Hmm. Sorry, which? Okay, okay. Last four formulas, these four formulas, right? Hello? Yeah, yeah. So what is the doubt? Yeah, so actually it has a very long derivation. I can do that, but due to limitation of time, I was not able to do the derivation. But yeah, I mean, for the exam perspective, you don't need to, I mean, like, completely remember this derivation. You just need to have this formula in your minds because there will be not lot of numerical problems that you will be able to solve using these formulas. Yeah, maybe if time permits, in the next week I'll try to do the derivation also if it is required. Yeah, sure. Yeah. So anyone having any doubts? Otherwise, we can wrap up. I mean, I do have some more problems, but yeah, I think we can do it in the next lecture. So next lecture, as you can see, we'll be starting with the PN junction device. There we will see. So currently, what we are doing is we are doing just making the band structures of only a single type of silicon, like it is either N or P. So in PN junction, we have a single silicon bar in which we have both types of impurity. So we'll see how the band structure compared to the picture and all of those things. So do attend the next week also because it is again very important to understand these type of devices. And yeah, if you don't have any doubts, I think we can wrap up the lecture for today. Maybe I can stop the recording.